These notes are on 1-3, which is about the types of relationships mathematically that we use in physics most often, how to graph them, and how to recognize them even when they are not in X's and Y's. Okay, so the most simple of all would be linear, right? And that goes for both positive and negative slope. So if you were drawing those, you would have, up and to the right or down and to the right. Usually we're sticking in quadrants 1 and 4 often because often we're graphing versus time and there are only positive times. And I am going to ask you not to use the word direct. I've seen students use the word direct to talk about lines with positive slope, but then I often get confused because they often use that word for quadratic too. So please nix that word in this class. When you have an equation, of course, y equals mx plus b is the format for that in math class, right? But in physics, we're going to use variables that stand for what we're measuring. So, for instance, if we're talking about x as like a location on a number line, okay, then that changes. So we might locate where is something located as time goes by. So then x goes on the left-hand side, and we might talk about where it is, like its speed and as time goes by, and its initial velocity and all this other position. So the important thing is that you look at the variables that are changing and the things that are not. So if I asked you, what is the relationship between x and t if the other things aren't changing? Well, then it's just like y and x if the other things aren't changing. And when t goes up, x might go up if this number is positive. If if this number is negative, then it will look more like this. It'll be linear with a negative slope. Okay, but those have a linear relationship with each other. And really, there's no other way to describe it, in my opinion. It's just a line or it's linear. Okay, another very common one is a quadratic relationship. So in physics, sometimes we have like half the parabola. Sometimes we have the entire parabola, like upside down. There are so many possibilities, but usually that's the only type of polynomial. Like we're not doing like to the third power or the fourth power, okay? Once in a while we would have like a square root, but quadratic is the most common. And in math, you learned y equals ax squared plus bx plus c. Okay, but again, in physics, we're going to substitute letters that stand for what they're measuring. So if we were talking about, again, where is this thing with respect to time if time is squared? So then you might have like something like 1/2 a t squared, okay, plus blah, 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 blah. Well, I can tell here, if I ask you the relationship between x and t, and a is just a number, then it's a quadratic relationship because x is on the left-hand side, t is on the right-hand side, and t is squared. So it's just like the relationship between y and x in the equation above, okay? And the name for this shape is parabolic, or it is a parabola. Okay. And then the third most common one is inverse. This would be a situation when the function would approach an asymptote And as the x variable gets larger, then the y variable approaches an asymptote. Usually we're talking about it would approach 0. Ooh, that looks horrible. Let me try that again. That's not much better. I hope you have a better steady your hand. Okay, so in math class, you would have studied this as y is some number a over x, or a times x to the negative 1, right? In physics, it could be like second semester, we're going to study current, which is, we use the letter I, and we say that equals voltage over resistance. So the relationship between I and R is an inverse relationship. If I make R really big, I will get really small. Okay? That's a special relationship. It's never going to go back up like a parabola would. Oh, sorry. And then the shape of this is a hyperbola, or is that how you say it? Or hyperbolic. Okay. And then when you graph in science, there are etiquette rules, and you've learned these in other classes, but let's review them. The independent variable, which I change, that's like the cause, okay? Something I do in the experiment as the experimenter is the variable that goes on the x. And then the effect, or the dependent variable, what happens as a result, goes on the y, typically. Sometimes there's exceptions to that rule. But we're going to stick with that unless I tell you otherwise. And then when you title it, you must mention both variables. You can make a nice long title. I really like those. If you're going to take a shortcut and be lazy, you must follow this rule. Like, if you're not going to say how the time you spend studying affects your test score, then you must say test score versus study time. You cannot do it the other way around. I didn't make up the rule, but sorry. Okay, and then label your axes with units. Okay. In science, we don't connect the dots. If it looks like it's supposed to be a curve, you're trying to figure out what kind of curve. If it's linear, you try to make a line that goes like sort of between all the dots. If it's linear, you can find the slope, okay? And that will mean something. So if we go back to my made up experiment, like you had people study for different times and then they took a test. Well, did that help them or not? So let's pretend that the slope of your line was rise over run, and they got it went up by 1% every 10 minutes. Okay, so then I'm going to ask you on the test to interpret that kind of thing. So you would say for every 10 minutes of study time, the test score increased by 1%. Remember, you want to say the cause first and then the effect. Okay? And the effect is up on top in the slope. You would never say for every 1% this test score went up, the student went home and studied 10 minutes extra. Well, they took the test already. Okay. And then, okay, we'll practice this in class. So that takes care of tonight's notes. And I will see you in class.